We present an autonomous class manipulation framework with physics-aware regularization and safety constraints. The class manipulation task is formulated as a constraint optimization problem where L is the control objective and C is the safety constraint. We propose and analyze an obstacle avoidance safety constraint where we sum over all particles along trajectory and collect all the negative distances offset by delta. Delta here is a safety threshold to control how much we want to avoid the obstacle. On the right, we show the obstacle avoidance behavior and plot the function we use to collect all the negative values. We first run the experiment with delta equals 0.05. The result trajectory passes through the opening of the U-shaped obstacle and can move the class to the target location without collision. We then repeat the experiment with delta equals 0.4. This time, the trajectory is more conservative and goes around the obstacle. To show the feasibility of the trajectory, we feed it to an IK solver and test it on DVRK robot. The loss we use is composed of target loss, trajectory irregularity, and potential energy. To understand how these regularization terms affect result trajectories, we did an additional ablation study. When we only optimize the target loss, the result trajectory is irregular and causes excessive stretching. When we optimize target loss and trajectory irregularity, the trajectory is smooth, but there are still excessive stretching. If we optimize target loss and potential energy, there's minimum stretching, but the trajectory is irregular. Finally, if we optimize target loss with both regularization terms, we can have a smooth trajectory and have minimum stretching. Thanks for watching.